So we were just discussing the relationship between momentum and Newton's second law, and we said that force was equal to the rate of change of momentum. And I'm actually write it as dp dt, okay? Which means that the change in momentum, well, let's look at it like this, okay? If we were to take t and multiply it over to here, we find that dp is equal to the force times dt. Okay, so basically what this tells us is that the change in momentum is equal to the force times the time. Okay, and we're going to call this quantity force times time. This is called impulse. Okay, and this is another important quantity that's related to momentum. Okay, because this tells us how the momentum of an object is changing. Okay, and basically, if we were to integrate the change in momentum, so if we integrate this, say from whatever like the starting time is to whatever the final time is, and we do the same thing over here, okay, we get that, and we'll call impulse, we'll call it J. So this what we get here is that J, the impulse, is equal to the integral of f dt. Okay, and what that means is this. Okay, if we have, and so there's a couple ways I want to go here. First of all, if you remember from last chapter, we know that work is equal to the integral of f dx. Okay, so if we have a position dependent force and we integrate it, we can get work. But for this chapter, if we have a time dependent force, we get impulse or change in momentum. Work would be our change in kinetic energy. Impulse would be our change in momentum. So I want to highlight one quick thing here. These are two different methods of solving problems. Okay? When we are given information about the time that a force acts on something, it's helpful to use a momentum approach to solve a problem like that. If we're given information about a force acting over a certain distance, then we use work and energy to talk about it. Okay? There are two different methods, and time and distance are kind of clues for us to decide which method would be best. Now, for this chapter, we're going to be focused on impulse, okay, and using impulse to solve problems. But even as we do these, a lot of the problems that we're looking at could be solved using kinematics, could be solved potentially using energy as well. So anyway, impulse then is equal to the integral of f dt, and integral, if we remember from previous discussions, is equal to the area under a curve. So if this is a graph of force versus time, if we were to find this area, that would be equal to our impulse J, which is our change in momentum, or our change in mv. So if we know the momentum of something and we know the area under a graph, we can find out how that momentum changes if we have like the force time graph. Okay, so we're going to see a couple examples of that right now. Okay, so we're given a 50 Newton force acts on a 2 kilogram crate that starts from rest. How fast is the crate moving 4 seconds later? Alright, so we're given a force and a time, and that's a clue to me that we should look at this from the perspective of impulse and momentum. Well, if the object starts from rest, that would mean that the initial momentum of it is equal to 0. Alright, and we know that our change in momentum, or J, is equal to the integral of the force on the object with respect to time. Okay, well, we have a force, so I'm going to just graph this because this, remember, is also area under a graph. So if we have a 50 Newton force, okay, so we'll say 50 newtons that acts for 4 seconds. Okay, well, if we find this area, that's going to tell us what our change in momentum is. Okay, so if we find this area, all right, 50 newtons times 4 seconds, that's going to give us an area here of 200 Newton seconds. Okay, and this would be our change in momentum. Now before we continue, I see that we have this unit Newton seconds. Well, in order for us to add that, our initial momentum would be in kilogram meters per second. Now hopefully those are the same thing. Well, a Newton is a kilogram meter per second squared. Okay, so if we multiply that by seconds, this is going to cancel out with that, leaving us kilogram meters per second. Okay, so if I take my initial momentum and add to it my change in momentum, I should end up with my final momentum. Okay, so initial was 0, my change was 200, okay, which means the final momentum of this object would be 200 kilogram meters per second. Well, the next step to find out how fast it's moving, if that's our momentum, mv equals 200, we'll divide by our mass of 2 kilograms, okay, and find that the velocity of this object is now 100 meters per second. Okay, now I could have answered that same question by dividing the force by the mass and doing kinematics, okay, but this is another approach that we can use. Alright, I also want to point out this. So if this is a uniform force that doesn't change with respect to time, then impulse and change in momentum is just equal to F times t. Okay, or we can even say our average force times time. Okay? Alright, we're going to look at another question real quick. So let's say that we have a baseball with a mass of about 0.15 kilograms. I think this is right. Let me double check. Yeah, so we'll say 0.15 kilograms, and it's been thrown at a batter, let's say at a speed, or a velocity rather, and we'll make it negative because it's going towards the batter, and we'll say that away from the batter is positive. So let's say it's got a velocity of negative 40 meters per second, okay, which means that would be about maybe like around 90 miles per hour, okay? And let's say that the batter swings and hits the ball and it makes contact for about 2 milliseconds, okay? And during that time it has a peak force of about 20,000 newtons. Okay, now if we were to graph the force over time for a baseball and a bat, it might be kind of curved like this, maybe like more of a bell curve. But to make things simpler, we'll make it like a triangle. Okay, and so using all this information, we can actually figure out how fast the baseball is traveling after the collision. And the way we're going to do that is just by saying, well, the initial momentum plus the change in momentum, in this case our impulse, will give us our final momentum. Okay, so our initial momentum, 0.15 times negative 40, alright, that's going to be about negative 6 kilogram meters per second. Okay, we're going to find the area of this graph. It's a triangle, so area would be 1/2 times base times height. and we can use that to find what our final momentum would be for the ball. Okay, so finding the area of the graph, we get 20 Newton seconds, or 20 kilogram meters per second, giving us a final momentum of 14 kilogram meters per second. So then we can go ahead and find the velocity of the baseball, and in this example we end up with a velocity of about 93 meters per second. Now 93 meters per second is about 200 miles per hour, which means that I don't think baseballs go that fast. I think probably they go closer to, like on a home run or something, maybe closer to like 110 miles per hour. And so probably the amount of time here is a little bit bigger than it would really be. They probably don't collide for that long, and I think this force is a little bit high as well. All right. One last thing I want to point out for impulse is this. Okay. Remember that impulse is equal to our change in momentum. So change in momentum is equal to F times T. Okay, and this is applicable in collisions. Okay, so you can imagine dropping an egg onto a pillow and dropping an egg onto a concrete floor, and in one example the egg survives and the other it doesn't. Okay, in both examples the egg is actually experiencing the same change in momentum because it is slowed to a stop by the surface it hits. Okay, and so whether you're dropping an egg on a pillow or on the floor, we have the same change in momentum, but for some reason the egg that's dropped on the concrete floor breaks while the one that's dropped on the pillow doesn't. And so we can explain this concept using impulse, okay? Because we can find change in momentum, and that could be caused by a very large force in a very small amount of time, or it could be caused by a very small force in a very large amount of time. I mean, so think about it. Which of these would be the egg hitting the pillow, and which would be the egg hitting the concrete? Well, when we hit the pillow, we experience a very small force because the collision takes a longer amount of time. Whereas an egg hitting concrete is going to experience a very large force because that collision happens very fast. Okay? And so here's just a cartoon about it. You have a guy getting punched in the face, and one is kind of a slow collision, doesn't hurt him that bad, whereas here you have a very large force, a very short time. And he experienced the glove in both cases has the same change in momentum, but in each case he feels something slightly different because that force is what causes the damage. Okay?